Standard search tools often rank data based on simple relevance or keyword similarity. But in a laboratory setting, the goal is to identify which specific hypothesis is most likely to be correct. Discovery intelligence is designed to support this process by prioritizing the search for scientific signal. To do that, the system must navigate a profound limitation. Biological and chemical reality is just overwhelmingly complex. It is defined by noise, contradiction, missing context, and historical dependence. A system can never capture all of that perfectly. A representation is not the thing itself. It is a selected view of reality, a bounded, deliberate compression shaped for a specific task. Attempting to build a perfect digital mirror of this complexity is an epistemological trap. It leads to systemic bloat, where models choke on irrelevant noise while missing the actual signal. The actual objective is to build a mathematically useful and scientifically honest representation, one that extracts only the structure relevant to the problem at hand. Recognizing this compression is vital. It prevents the system from projecting false confidence over aspects of reality it cannot actually see or measure. Because a representation is compressed, its shape must be dictated entirely by the specific scientific decision it is trying to improve. We have to look at the downstream task. If prioritizing candidates for testing, the representation extracts one specific set of features, ignoring the rest. For estimating measurements or comparing belief states, the same underlying data requires a completely different perspective. The question we should ask is never, did we capture everything? The only operational question that matters is, did we capture what matters for this specific decision? Representation doesn't exist in a vacuum. It is only valid when explicitly linked to its purpose, its task, and the metrics used to evaluate it. There is a strong professional temptation to rely on a single, fixed representation, the monolithic foundation model approach. It is architecturally simple. In practice, scientific inputs are highly variable. One session might contain only bare molecular structures, while the next brings in deeply annotated assay contexts, prior evidence, and support history. Forcing these variables through a fixed architecture creates two severe failure modes. The first is underrepresentation. The system receives incredibly rich data, but remains structurally blind to it. Discarding nuance keeps predictive signal weak, while crude heuristics do the heavy lifting. The second failure mode is overassumption. This happens when sparse inputs are forced into a complex model built for rich data. The system hallucinates missing information, acting as if rich structure exists, projecting dangerous levels of false confidence. A single frozen representation guarantees failure at both extremes. To handle the variance of real scientific inputs, the architecture must abandon static models. Dynamic representation does not mean uncontrolled adaptation. The system cannot invent new latent spaces or representations on the fly. Uncontrolled runtime invention is fatal to a scientific system. It destroys version control, breaks comparability across sessions, and makes evaluation mathematically impossible because the meaning keeps shifting. The solution is governed dynamics. The system selects from a finite, approved set of representation profiles. Each profile is an explicit, versioned way of seeing the input. It defines exactly what tasks it supports, what inputs it requires, what fields are optional, and precisely how it degrades when data is weak. By categorizing representations into these explicit profiles, modeling assumptions are transformed from invisible biases into governable architectural objects. With multiple profiles available, the system needs a gating mechanism to manage them. We call this the router. When data enters the system, the router interrogates it. It checks the task type, assesses the richness of the input, and flags critical missingness. Based on that scan, the router dynamically snaps the optimal profile to the input, a structure-only profile for bare molecules, or a richer contextual profile when assay data exists. Crucially, the router records its logic. It logs exactly which profile was chosen, why it was selected, and what level of caution should accompany it. The router ensures discovery intelligence does not blindly output scores. The system retains a record of its own visibility, accounting for exactly how much evidence it could see before generating a result. This leads to the concept of representation support. the explicit tracking of how robust or thin the active representation actually is. Support states range from strongly supported when data is dense, down through context-limited, all the way to honest fallback profiles for thin inputs. Representation architecture is only useful if it alters downstream behavior. Weakness must influence decisions. Under strong support, the engine operates with high confidence, ranking aggressively and creating decisive separation between candidates. When support is thin, the system modulates its behavior. Aggressiveness drops, uncertainty widens. The system becomes far more likely to declare a comparison too close to call. Systemic doubt is a feature. An honest scientific system must penalize its own tendency toward overpromotion when relying on thin data. Because we cannot know in advance which representation is best, selecting one is a hypothesis. It is an approximation built on scientific judgment. Because it is a hypothesis, evaluation is the only way to prove a representation is actually useful, rather than just aesthetically pleasing. This means testing across multiple layers: task-level success, input condition limits, specific cohort behavior, and cross-session stability. Simple accuracy metrics are insufficient. We have to measure scientific plausibility, check how gracefully the model degrades with missing data, and ensure its failure modes are honest. Without this layered scrutiny, representation remains ungrounded intuition. Evaluation transforms it into rigorous science. A representation profile has an iterative life cycle. It is hypothesized, rigorously evaluated against tasks and subsets, compared against older versions, and only then considered for promotion. The promotion pipeline is strict. Profiles move from experimental to bounded use to preferred, ensuring controlled progress without freezing the entire system. Representation is never a solved equation. It is a sequence of hypotheses about what parts of reality matter, tested by the system, and eventually corrected by reality itself. Discovery intelligence succeeds by deliberately choosing explicit profiles, penalizing its own uncertainty, and never confusing the mathematical model with the reality it compresses.